Hello, Algebra 2. This is a lecture on section 10.2. 10.2 actually covers two different things, which would be combinations first up, and then the binomial expansion theorem. There's going to be two different lectures on this. The first one is just going to be combinations, and then focusing on the difference between combinations and the other methods previously taught in section 10.1, and then a separate lecture on the binomial expansion theorem. All right, so in 10.1, we talked about something called permutations. And remember, permutations is when you are selecting some objects. We use the letter R for that. We are selecting R objects from a group of N objects. And with permutations from the last unit, it said where order is important. And with combinations, that would be the opposite of that. In combinations, the order is not important. And I'm going to highlight that right there. The formula for combinations is going to be right here. We're going to use NCR, very similar to NPR from the previous lecture. The numerator is going to still be n factorial. And then with permutations, the denominator was n minus r factorial, this part. But with combinations, we're going to add this r factorial in addition in the denominator. However, just like with permutations, if you select math and then you go over to probability, you're going to see the combinations button on your TI graphing calculators. And so our calculators are going to be able to calculate the combinations that we would need. So that brings us to combinations versus permutations. In the quizzes and tests, I'm going to ask you just like how many winners, how many ways can we select the winners of a certain situation? And it's going to be up to you guys to decide if that's a combinations or permutation situation, and then come up with the answer by using your calculator, right? But come up with that answer that corresponds to whatever situation it is. And so it's going to be very important for you guys to decide if it's a combinations and a permutation or a permutations problem. I know it's not always about winners, but that's kind of like the go-to illustration that I have, your winners of a contest. The question that you have to ask yourself to help you decide if it's combinations or permutations is, do the order in which the winners are selected make a difference to the winners? So I can basically make one situation a combination, take a situation and make it a combination or a permutation situation by the way that I word basically the prizes. But the question you have to ask is, do the winners care which order they were selected when they won? So for example, in the last lecture, I talked about like a mathlete race, right? Where you have to like run a 10K then solve a math problem. A permutations example would say, hey, first place gets $500, second place gets $250, and third place gets $100. Okay, that would be a permutations example because the winners care which order they're selected. Okay, it matters to the winners which order they were placed in the race. Combinations, on the other hand, would be the same situation. The top three winners, let's say, instead of getting this prize pool, I'm going to say the top three winners get to go on to sections mathlete race. Okay. Now, the winners don't care which order they're selected. If my question was how many different groups of three could move on to sections, that would be combinations because it's the exact same, if Becky and Martin and Gia all take first, second, and third, or if Martin finished first and Becky finished second and Gia finished third, that's the exact same thing. It didn't make a new group of winners. And so that's when you would be talking about a combinations example. Okay, the winners don't care which order they're selected to be winners. They only care that they were selected to be winners. Permutations, I want to be first, okay, or I want to be in a specific order. So here would be an example in a lottery. 4 winners will get equal prizes. If 20 people enter the lottery, how many groups of 4 ways could be chosen? The first thing you have to ask yourself is, do the orders care which order they're selected? Do the winners care which order they're selected? And they certainly don't. All the winners get the same prize. Now, people absolutely care. This is the confusing part. People accidentally think of it this way a lot of times. They're like, yes, it matters if they win or not, so then it must be permutations. That's wrong. Okay, I'm only asking about the winners now. Do they care which order they were selected in? Okay, because they're all getting equal prizes, they don't. This is a combinations problem. So there are 20 total people. We're going to use combinations to select 4 of them. So you do 20, 20, math, go over to prob, 3, 4, and you would find out that there are 4,845 ways to select 4 people out of 20 in which the order of the 4 chosen, okay, their order in the top 4 don't matter. How about this one? How many ways can 11 books be arranged on a bookshelf? If we are using all the different ways that we learned in 10.1, we have 11 objects, and we're going to select all 11 of them. Hopefully that is prompting factorial in your mind. So you go 11, and then just slide over to PROV, and then factorial is the exclamation point. 11 factorial is that number. Okay, there are a lot of ways that you can select 11 books in, arrange 11 books on a bookshelf. It would technically be also the same thing to say, okay, this is a permutations problem, because the order, if I switch 2 books, I've now made a new arrangement of the 11, and there's 11 total books, so I'm selecting all 11. That's going to give you the exact same answer. And so I wouldn't really care which way you thought of it. If you thought of it as using factorial, or if you thought of it as using 11p11, you would have gotten the same answer. Another situation on a 15-item test. The first 5 have 4 choices. The next 5 have 3 choices, and then the last 5 are true or false. If Johnny answers 2, 7, and 10 correctly and guesses on all the others, how many ways can he complete the test? Okay, so in this particular scenario, this one is actually going to use the fundamental counting principle, and it's a lot like the license plate example from 10.1. So if you think of the first question on the test, there are 4 different ways that Johnny can answer the first question. And then the second question, we know that he's getting right. So we're going to not care about the second question. In the third question, there are 4 different ways. In the fourth question, there are 4 different ways. In the fifth question, there are 4 different ways. Question number 6, there are 3 different ways 3 different options that Johnny could pick. Question number 7, he's got right. Question number 8, 9, and 10. Question number 11, Johnny 10, 1, 5, 6, 7 is right, 8, 9, 10. So 10 doesn't matter here. And then we have 11 through 15 are all 2 different options. 2 times 2 times 2 times 2 times 2. And so just like the license plate example, we're going to multiply all these things together. We actually have 4 to the 3rd power, 4 to the 4th power, times 3 to the 3rd power, times 2 to the 5th power. That's how many ways that Johnny could complete this test, given those specific parameters. 221,184. And this last example is also a fundamental counting principle example. We want to make a 3-letter word code out of B, C, D, E, and F, and repetition of a letter is allowed. And so we're talking about 3-letter word codes, so 1, 2, 3. Repetition is allowed. So the first event can occur in 1, 2, 3, 4, 5 ways, and so can event 2, and so can event 3. So we would just multiply these things and get 125, and that would be the number of ways that you could arrange 3 letters out of those given choices. So this is what I want to talk about with combinations. And section 10.2 part B will be on the binomial expansion theorem. Please let me know if you have any questions.